Alright guys, this is Mr. B here, and I'm going to be going over this series circuits worksheet with you. Now I already recorded this, so I'm just going to be talking over this video, because I actually recorded it once and I didn't realize that there was no sound. So looking at this first diagram, number one, we have electrical devices, and they want us to ask whether these are connected in series or parallel. So if we draw a line from one side of the battery to the other, and we see that we can do it in one path, this would be considered a series circuit. But you'll notice that we can actually draw multiple lines from one side of the battery to the other. The red line goes through the voltmeter. The middle blue one can go through the light bulb, or this green one can go through, I believe that's a speaker. So because we have multiple lines here that can go around from one side of the battery to the other, this would be considered a parallel circuit. Whereas if we look at the one on the right hand side and we draw a line from one side of the battery to the other, again we'll notice that in this one we can only do it one way. There's no other way to go from one side of the battery to the other. There's only one line, which means that this would be considered a series circuit. So looking then at number two, this shows two electric circuits diagram below. And for each one, they want us to indicate which devices are connected in series and which are connected in parallel. So again, if we draw a line from one side of the battery to the other and look to see what devices we go through, we'll notice that when we draw this line, we have to go through the ammeter and the resistor, but then we get to this point where it's going to split between the bulb and the speaker. So the ammeter and the resistor are going to be in series with each other because we have to go through both of those. We don't really have a choice. However, when we get to the bulb and the speaker, we're going to notice that we can split here. We can decide to either go up through the bulb, which then can connect us to the other side of the battery, or we can decide to go down through the speaker, which will then connect us to the other side of the battery, but we can't do both. We have to go through one or the other, which means that the light bulb and the speaker would be set up in parallel to each other, not series, because again, we have multiple paths that we can take. We don't have to take both, we can only take one. So looking at the one on the right side, again, if we draw a line that goes through the objects, we'll see here that we have to go through the speaker and the ammeter. We don't have a choice, which means that these would be in series with each other because there's really only one path for us to take. However, again, when we get to the light bulb and the resistor, it splits. We can choose to either go up through the light bulb to get to the other side of the battery, or we can choose to go down through the resistor to get to the other side of the battery, but we can't go through both, which means that these are going to be set up in parallel with each other, not series, because again, we have a choice, and we can only go through one or the other. We can't go through both. Okay, so looking down here at number three, fill in the table to indicate the manner in which series and parallel circuits differ. So the pathway by which charge loops around the circuit is characterized by, in a series circuit, this would be one pathway. Again, there's only one way for us to go around the circuit, but in a parallel circuit, it would be two or more pathways. And we can see here by looking up at the top diagram that, again, we have multiple pathways. In this case, we actually had three pathways, not just two. That's why we have two or more. So parallel circuits, usually there's multiple ways to do it. Letter B, if one light bulb goes out, the other light bulbs, in a series circuit, they would go out. So again, if we look at the diagram up above, if we were to remove one of those light bulbs, we would see that there would no longer be a path for the charges to go from one side of the battery to the other. So all of the items on that circuit would go out because we would remove essentially that connection. Whereas in a parallel circuit, if we were to remove one of the objects, the other ones would stay on just fine because, again, there are multiple pathways for them to take. So just because one object is gone, then that just means they have to go a different way. So again, if we were to remove the voltmeter in this upper left one, we could still go through the light bulb, or we could go down through the speaker, which means that we could still connect to the other side of the battery, and therefore those objects would stay on and not everything would turn off. So letter C, as the number of resistors is increased, the overall current in a series circuit, the overall current then would also, the overall current in this case would decrease. And the reason why it would decrease is by adding more objects on the circuit, or more resistors, you're essentially creating more friction for the charges to have to flow through, which means that overall they're going to slow down. And the current, again, is the number of charges that are flowing through a wire at any given time. So more resistors, more objects on the circuit would mean that there's more friction, which ultimately means that they're going to slow down because there's more stuff for them to go through. But in a parallel circuit, it's actually the opposite. By adding more resistors, you're actually going to be increasing the overall current, which seems strange because, again, you would add more objects onto the line. So you might think like, well, that means that things should slow down, right? It's actually the opposite. And the reason is by adding more resistors on a parallel circuit, you're actually increasing the number of pathways that those things can take. So here we could go through the light bulb or the resistor. However, if we added a third object onto this circuit, and it could be maybe a motor or something else, we now have another path for those charges to take, which is essentially going to allow more of them to go down the circuit at any given time, which is therefore going to increase our current, not decrease. So again, these two are opposites, but by adding more resistors onto a parallel circuit, you are increasing the overall current rather than decreasing it. As for the last one, as the number of resistors is increased, the overall resistance in a series circuit would also increase. Again, by adding more resistors, you are also then increasing the total resistance. You're adding more friction onto the circuit. And likewise with a parallel circuit, by adding more resistors onto the circuit, you are going to be decreasing the overall resistance because you are creating more pathways for those objects to take, which means there's going to be less friction and therefore less resistance. So, all right, scrolling down here to look at number 4. The following diagrams represent circuits consisting of two electrical devices connected in series. For each one, fill in the blanks to show the voltage drop across the designated device. So in diagram A, we have a 120 volt battery, and we have two objects on this circuit. One light bulb is going to be using 80 volts, and the question is how much is the other one going to use? Well, the voltage that the battery supplies has to be used among both of these objects. So if the one light bulb uses 80 volts, that means that the other one is going to have to use 40 volts because total 120 volts have to be used between both light bulbs. So the difference, of course, between 120 and 80 would be 40. And it is a minus because we are showing that we are losing 40 volts as it goes through that first light bulb. Looking at the other one, we have a 12 volt battery. We have 3 total objects, 2 of which they're telling us the voltage. So one is 3 volts and the other is 4, which means between these we are using a total of 7, which means that the object that is unknown here would have a total of 5 volts being used because the difference between 12 and 7 is 5. And we are going to have a negative there to show that we are losing 5 volts because that object, of course, is going to be using voltage to get powered. So this one's pretty basic. We're just essentially doing some simple addition and subtraction. All right, looking at number 5. Consider the following 2 diagrams of series circuits. For each diagram, use arrows to indicate the direction of the conventional current, then make comparisons of the voltage and the current at the designated points for each diagram. Okay, so the first thing we're going to do is we're going to draw the direction that the current is traveling. Typically in a conventional circuit, we would show that the charge is going to move from the positive side of the battery to the negative side of the battery. So we want to draw a line, or essentially, the direction of charge flow using arrows to go from positive to negative, like this. In diagram B, we see that they have flipped the battery, so it's going to be going the other way around, positive side to the negative side. Okay, same premise, obviously, but the battery's just been flipped, so we just have to look at that. As for the voltage, so the next part is to determine if the voltage is greater at A or at G. So let's assume that we maybe have a 10 volt battery here, and we want to look at what the voltage would be at A compared to G. So we have 3 light bulbs. Each one has to use all of the voltage of the battery. And actually, for this sake, let's actually change this to 12 volts because it makes the math a little bit easier. So let's assume we have 12 volts, which means that the first battery, or the first light bulb, is going to use 4 volts. The second light bulb is also going to use 4 volts, and the third object, which I think is a speaker, is going to use 4 volts. So we see that we are using a total of 12 volts among all 3 objects. So at A, it would have a voltage of 12 because at this point it hasn't gone through any objects yet. Whereas at G, it's going to be 0 volts because it has traveled through all of the objects on the circuit. So that means that the voltage at A is going to be larger than G because at A, nothing has been used yet, but at G, we've gone through all of the objects. As for at point B, at this point, again, it still has not gone through any objects, so it would have 12 volts. Now, it has gone down the wire, but it hasn't gone through anything on that wire, so no voltage has been used. It hasn't powered anything yet, so it would have 12 volts. Whereas at C, location C here, we've used 4 volts to power the first light bulb, so that is only going to have 8 volts at that point, which means that the voltage at B is going to be larger than C because we haven't used any yet at point B, but at point C we've gone through the light bulb and used 4. So then looking at point B, voltage B compared to voltage F, again at point B we know that we haven't used any voltage yet, so we're at 12. Whereas at point F it would be 0 because we've gone through all 3 objects, 2 light bulbs and the speaker, so we've used all 12 volts and we have 0 volts at point F. Therefore, the voltage at point B is going to be greater than the voltage at point F. So we're going to put that down here in a second. And then lastly, as for the current, so here we didn't put in a number for the current, but let's just assume that we maybe have a current of 12 amps, just to make it simple. And in this case, the current at point A and the current at point G are going to be the same because it's a series circuit. So the current is how many electrons or charges are flowing through your wires in the circuit. And the current is not going to change because it has to travel down the wire no matter what. And it doesn't matter how many objects are on the circuit, the current is going to be the same and it's going to be continuous the whole time. So current at A and G are going to be equal because current doesn't have any effect with the light bulbs. So at this point, we're going to look at diagram B. If you'd like, you could pause the video and see if you can solve it on your own. And then we're going to continue here, and I'll solve it next, and you can take a look to see if you got it correct. So, looking at diagram B, the first question is, what is the voltage at A compared to F? So, again, let's assume we have maybe a 12-volt battery, just like we did before. At point A, we see that we have gone through all of the objects on the circuit, so we would have 0 volts. Whereas at point F, we haven't gone through anything yet, so we would have 12 volts still, which means that the voltage at F is going to be greater than the voltage at A, because again, at F, we haven't gone through any objects, whereas at point A, we've gone through all 3 objects. As for the voltage at B compared to C, at B, again, we've gone through all of the objects, so we have 0 volts. Whereas at point C, we've only gone through 1 object, and that is the 1 light bulb. So at point C, we would have 8 volts. 4 volts would have been used in the first light bulb, but that's it, because we haven't gone through the resistor yet, or the object that's right after point C. So point C, again, is going to have a larger voltage than point B. Once we do go through that object, we would have used 4 volts, so we'd have 4 volts on the other side, but before we go through it at point C, we have 8 volts. So again, point C is going to have greater voltage than point B. As to voltage at D compared to F, at D we would have 12 volts because we haven't gone through any objects yet, and at point F we would have 12 volts because again, we have not gone through any objects. Now again, we have gone through the wire from F to D, but there was no objects on that wire, which means that we haven't used any voltage. So at point D and F, they're going to be equal to each other because again, no voltage has been used. They both have 12. And then as for the current at point A compared to point F, just like before, the current is going to be the same throughout the entire circuit, so these would be equal. The current and the number of items on the circuit have no effect on the current. So. Okay, looking at number 5, express your understanding of equivalent resistance by filling in the blanks. So having 2 4-ohm resistors in series is equivalent to having one 8-ohm resistor. So if it is a series circuit, we know that the total resistance on a series circuit is basically just going to be adding up all the resistance of all the resistors on it. So we would just add resistor 1 plus resistor 2 plus resistor 3, etc., etc., etc. If we have two 4 ohm resistors, we know that 4 plus 4 equals 8, so that one's pretty simple. Having three 4 ohm resistors in series is then equivalent to having one 12 ohm resistor, because we know that 4 plus 4 plus 4 equals 12. So again, pretty simple, which means that the very last one, having four 4 ohm resistors, then would be equivalent to having one 16 ohm resistor, because 4 plus 4 plus 4 plus 4 equals 16. So that one again is pretty simple, just by adding together all the resistors. So the last one here is number 6, true or false. 3 light bulbs are connected in series. The filament of one of the light bulbs burns out. The remaining 2 light bulbs will still be lit, yet their brightness will be noticeably less. So if they're connected in series and one of the light bulbs burns out, that would mean that all of these would burn out. So this would be a false statement. They would not remain lit. Their brightness would not be noticeably less. They would not be bright at all. They would not even turn on, because in a series circuit, if one burns out, they all go out. All right, so finally then, looking at these last questions, number 7, analyze the following circuit and determine the equivalent or total resistance, then determine the current at the amp meter location. And the amp meter is the A there. So, all right, so first off, our total, so total resistance. We're going to need to use Ohm's law to solve this problem. So we know that that is voltage equals current times resistance, or V equals I times R. So the first thing we want to do is solve for the total resistance. We see that we have 3 resistors that are each 2 ohms. So 2 plus 2 plus 2 gives us a total of 6 ohms of resistance. As for I, which is the current, again, we're going to need to use Ohm's law here to solve that, which means I'm going to have to rearrange this equation in terms of I. So here I have it written in terms of V, but if we rearrange this in terms of I, we find that I, which is current, is equal to voltage divided by resistance. So we know that the voltage is 12 volts. We know that the resistance is 6 ohms. So the current in this case would be 2 amps, because 12 divided by 6 is 2. So using that then, take a look at circuit B. You can pause the video and see if you can solve it, and then I'll go over it here in a second. Okay, so looking at the total resistance here, we see that we have 3 resistors that are 6, 4, and 2. So adding those together, 6 plus 4 plus 2 gives us 12 ohms of total resistance. As for the current, again, we know that current is voltage divided by resistance. The voltage in this case is 6 volts. We know that the total resistance is 12 ohms, which means that the current in this case would be 0.5 amps, or half of an amp. 6 divided by 12 is 1/2. So that one's pretty simple, again, using the same thing as this previous problem. So looking at number 8, for the following diagram, utilize the concept of equivalent resistance and Ohm's law in order to fill in the blank. So in this case, they now want us to solve for this missing spot, which is current. So to solve for current, again, we're going to need to use Ohm's law. They are giving us the resistance of these objects, so we can find the total resistance. So let's do that first. We know that our total is going to be equal to 30 plus 30, so that is 60 ohms. They also are telling us the voltage of the battery, so V is going to be equal to 120 volts, which means then to solve for I, we know that current I is going to be equal to voltage divided by resistance. In this case, the voltage is 120 volts. The resistance is 60 ohms. So 120 divided by 60 gives us a total of 2 amps. So we're here kind of utilizing information from the last problem to solve for this one. So then looking at the one to the right, again, you can pause the video, see if you can solve. Here, though, we're trying to solve for this missing resistance piece. In this case, again, they're giving us voltage of 24 volts, so we can write that down. They're also now giving us the current, which is 2 amps. So I is going to be equal to 2A, or 2 amps. And now we're going to be solving for resistance. So I want to rearrange my equation in terms of R, which I haven't written it that way yet. So we know that R is going to be equal to V divided by I. In this case, we know that V is 24 volts. We know that I is going to be 2 amps. And this is going to give us the total resistance of all of the resistors. So this is going to give us 12 ohms of resistance. But they're only asking for us to solve for one of the resistors. So we know that 4 plus 2 plus blank is going to be equal to 12. So with the ones that they've already given us, we know that 4 plus 2 gives us 6 ohms of resistance. And we know that total, we have 12 ohms of resistance, which means that this missing one has to be also 6 ohms, because 6 ohms plus 6 ohms gives us a total of 12 ohms. So that is how we're going to solve that problem. All right, looking then down at the last two, again, utilize maybe these first two for circuit A and circuit B as examples if you want to pause the video again and try to solve these on your own, and then we're going to go over them in a second and see if you get them right. Okay, so starting off, they do give us a voltage of 24 volts on the battery. They give us a current of 2.4 amps, and they're asking us to find the resistance of one resistor. Again, we know that resistance is voltage divided by current, V over I. So 24 volts divided by 2.4 amps. This is going to give us a total resistance of 10 ohms. And again, this is going to be a total resistance because it is multiple resistors added together. So we're going to write down that R is equal to 10 ohms. This is the total. So we know that 2 plus 4 plus 2 plus blank equals 10. So this would be then giving us 4 plus 2, which is 8, which means that the missing piece is going to be 2 ohms of resistance, because again we had a total of 10. As for then circuit D, they are giving us the current, which is 3 amps. They're also giving us a total resistance of 6 ohms, 2 plus 2 plus 2, which is 6 ohms. And they're asking us to solve for voltage. And we know that voltage is going to be equal to I times R. So I, in this case, is going to be 3 amps. We know that R is also going to be 6 ohms, which means that the voltage on the battery will be 18 volts. 3 times 6 equals 18, and that's what they were looking for. So hopefully this helps and explains a little bit on how to do some of this stuff. Look at these as some examples and some problems. And as always, if you have any questions, you can always email me and ask for more help that way. Or there are videos on Schoology that you can watch and do that way. So thanks for watching.